Hello and welcome everyone. I'm here with Damien and he's here to talk with us about development with Project Esky, and handing over to you, Damien, right away. It looks like we can't hear you right now, so we'll have to do some troubleshooting first. What could be? Could it be that your mic is muted?
No.
Now we can hear you. Perfect.
You can hear me now?
Yes.
Okay, that works. That works for me. So for those that are joining me live via Facebook, you're probably wondering why it looks like I'm talking to myself. I'm actually live casting this via StreamYard as part of the Global XR Talks. Let me get started straight away then. If my global hotkeys were working. So welcome to Development with Project Esky. My name is Dr. Damien Rampapis. I'm a researcher at the University of South Australia. So I'll start off a little bit with who am I? Well, I already announced myself. I'm 28 years old. I'm a software veteran for over 19 years. And as you can already tell from the headgear and the photo, probably plugged into the matrix far too much. So the structure of today's talk will be as follows. One, the what, why, and how Project Esky, the software architecture of Project Esky, development with Project Esky, including the first steps, your typical workflow, and networking with Project Esky, then some demonstrations and code walkthroughs. Finally, we'll have a bit of time for a little bit of Q&A for those that are chiming in. For those that are watching live via Facebook, I'm very happy for you to just leave your comments in the view, and double check that Facebook's actually live streaming this on a public. All right, now that we're back to that, so let's start with development with Project Esky, as in a quick intro to Esky. So what is Esky? Project Esky aims to combine any AR HMD, most notably the Project North Star, like the one that's sitting on my forehead right now, with a low-level renderer. In my case, I used Microsoft DirectX, but Esky also has an OpenGL renderer, a low-level tracker API integrating the Intel T265/T261 as seen in the DECX variant of Project North Star, or the Stereolab Z series 6-degree freedom head trackers, as well as mirror networking bundled into the Unity game engine. And we have got wrappers prepared for the Unreal Engine, which are coming soon. Now, this is all integrated in a nice and easy way for the Mixed Reality Toolkit. So let me start with why Esky. So Esky allows for the integration of any HMD because of the nature of its low-level API references. It includes the hand interactions out of the box, as we're using typically the Leap Motion hand controller, but because of the MRTK integration, we have the HoloLens and HoloLens 2 hand tracking integrated. We have spatial mapping with the Z camera series, like the one that's integrated into my Project North Star at the moment, and a 6-degree of freedom head tracking unit. So again, some people have the DECX variant of Project North Star. That includes the T265 or T261 from Intel, or the Z tracker as what's displaying on my head. We also have relocalization and authoring kits built into Project Esky, and that's very important because this is one of the hardest parts to do with creating an XR scene. Finally, this is a minimal SDK. We wanted to remove as much of the bloat from the SDK to allow the developers to do what they want with it rather than having to fight with the system. Not to mention that this code is completely open source without any license restrictions. We wanted people to have complete freedom to do whatever they wanted with the SDK. This also includes an MRTK integration, which allows us to essentially develop using Project North Star and rapidly deploy to either OpenVR headsets, HoloLens headsets, the Meta 2. We have a Meta 2 sitting in our laboratory right now that's enabled with Project Esky. The main point of this project, though, is to significantly accelerate the development rate of these XR applications. Core point of this one is I presented several demonstrations at ISMA and ISS over the last couple of days, most of which were developed anywhere between the time span of a single day to 5 days to less than 1 month with a series of undergraduate students. And this is important because these undergraduate students had never worked with augmented reality, mixed reality before. So let's get into the point of how Esky. Now, Brian has already given a quick introduction on the calibration procedures behind the North Star headset. But typically, for any headset that we wish to use, we need to calculate its HMD distortion so that way all the lines that appear in front of us appear straight. So for this, they have a version of calibration called binary structured light homography, which allows us to calculate the curvature of the lens of our display. Then once we've done this, we need to calculate the between sensor alignment. So there's a series of head trackers, hand trackers connected to our headset. We need to know their relative offsets to the user's eyes. For this, we've got 2 methods built into Project Esky, the first of which is a hand alignment tool. And the second, whilst not directly built into Project Esky, is available via the Project North Star webpage and Discord, which allows us to use fiducial markers, which are tracked and then are able to allow us to calculate very precisely this between sensor alignment. So moving a bit forward, I'll briefly touch over this now, but go back into more detail later. How does one develop with Esky? Now, actually, there's a series of pre-configured rigs within Unity game engine as prefabs that one can quickly drag and drop into a scene. In my case, seeing as I've got a Z tracker attached to my forehead, I'm using a pre-configured Z rig. Then on top of this, we have an out-of-the-box MRTK integration, which includes the profiles for Esky and our Leap Motion hand alignment calibration series. So the point of this is that our pre-configured rigs are configured in a way that has a single tracker, a hand tracking unit, a rig center, which is marked as our Esky origin for the HMD, and our Esky origins for the left hand and the right hand. So development with Project Esky. Let's get a little bit technical as to what's going on behind the scenes. So the overview of the Esky SDK is at the top level, we've got our game engine, which is the Esky SDK integrated into it. The Esky SDK interacts with several Esky high-level APIs, which then integrate with the Esky low-level APIs that communicate directly with the hardware. Essentially, you would only be working with the Esky SDK and would not need to care about what the high-level APIs or low-level APIs are doing, therefore taking away a lot of the strain of this kind of development. So the software architecture is as follows. So we have a high-level API, which is a game engine wrapper, which consists of an Esky renderer and an Esky tracker. The Esky renderer takes these native eye texture pointers for the cameras that render our left and right eyes, and then pumps these directly into a separate spun-off instance of a renderer, which is displayed on screen. Now, this renderer is available as either DirectX or OpenGL. The reason for this is because we're able to get very low latency texture parsing free whilst displaying this as a separate instance, allowing us to render this at a very high frame rate and therefore later integrate in temporal warping. Additionally, this includes the Esky tracker, which takes care of the map loading and saving as what we call Esky map blobs, and includes code for local initialization, 6-degree freedom pose receiving, spatial mapping mesh grabbing, image previews, and map loading. Following on, so the Esky SDK, as I mentioned, wraps over several hardware components. In our case, they're HMD hardware, and for input, the Leap Motion controller or the OpenVR controllers or the HoloLens 2 hand tracking as passed through the Esky MRTK connectors, which then hook up to the MRTK and are tagged with our various Esky origins. So for the head-mounted display, the left hand and the right hand. Now, all of this passes into the Esky utilities, which is ideally what your code would interact with, rather than interacting with the hardware directly. So ideally, your code would be built on top of the Esky utilities or the MRTK integration that comes with Esky. So the SEXR scene graph is pretty simple and straightforward. So given your typical AR scene as me fighting, entering this fighting pose or looking at a coffee in front of me, we have a Esky anchor, which is a ambiguous point within our scene, and an Esky tracking origin. Additionally, we have some Esky anchor content, and I'll go into a little more detail on the differences between anchor, tracking origin, and anchor content. But really, we have our rig center as our Esky origin, HMD. And as I mentioned, we have our left hand and our right hand. So the XR scene graph works as follows. We consider the Esky anchor as the root of our scene, the virtual environment that we're going to be developing with. Then we synchronize all of our content and the user in accordance to the Esky tracking origin, which is usually placed at the same place as our Esky anchor. So really, we have a user as a transformation matrix from the Esky tracking origin. And then within that, the child objects, we have the Esky origin, the HMD, and our left hand and right hand. Now, let's go into development with Project Esky a little bit, as in creating an Esky-enabled application. So to start with, your typical Esky workflow is you set up your scene, typically using the pre-configured scenes and prefabs that we have. We create an Esky anchor within the scene. We add content and attach Esky anchor content scripts to each part that we want to integrate. Then map the area or use the spatial mapping mesh. And then whilst live, we're able to author content and save the map. Once the map's saved, you should be able to rapidly be able to deploy and demo this application. So let's go ahead and dive a little bit into the code environment. Now, I'm actually going to be doing something a little bit strange and going through the code of the demonstrations that I presented yesterday. So I'm going to open up the scene a little bit, switch over here. Now, I do apologize that my computer is running a little slow. I am running a few computers at the same, a few screens at the same time. So here we have our typical Unity scene, which has been pre-configured for a Esky Live demo. Now, as I mentioned, we have a series of prefabs that have been pre-configured so you can drag and drop and be ready to go. In our case, we have a North Star rig specifically for the Z. Now, this includes the hand model manager for the Leap Motion SDK attached to it, as well as a single script which handles the Esky tracker for the Z, and a single script which handles the Esky native DirectX renderer, which essentially takes the left and right eye cameras and displays them directly on the screen. Finally, we have the marked Esky HMD origin, which is where we can attach head content to. So I'm just going to quickly load this scene up and hit play to make sure I haven't broken anything. Pop the headset down. Now, in the bottom left, you're seeing essentially a live view using the video texture see-through that's afforded by the Z SDK. So you can see as I rotate my head around throughout the scene, the content is updated and placed into the environment based on the head pose. Additionally, my hands, if I bring them into the scene, you notice that there's some content attached to my left and right hand. Now, I'll select one of those content menus. So we see in the left-hand menu, as I move it around, it stays attached. Now, this is because it's using what's called a follow Esky origin script, which is basically configured to be able to follow the marked left-hand target with 6 degrees of freedom. Now, we have several follow types. First is the 6 degrees of freedom, as in rotation, translation. We also have 3 degree of freedom translation, a 3 degree of freedom rotation, as in we only apply the translation and rotation of the object, or the 4 degree of freedom Y rotation, which essentially takes the transform's pose and applies it only from the translation and the Y rotation axis. Now, why this is important is for me to bring up this menu. So if I open this window up here, we'll notice that as I rotate my head around, if I rotate my head vertically, the object in the scene stays attached without rotating on the x-axis. But if I rotate on my y-axis, the screen actually follows me. And if I move my head back and forth, the screen follows my XYZ translation. Now, additionally, there are some other utilities that we have available to Esky. One of them is being used by this little floating window monitor in front of me right now. So if I actually take a look at the canvas object, we can see that there's a smooth follow Esky origin script attached to it. Now, what this essentially does is the same thing as our follow origin that's being attached to my left hand and my right hand, with one exception. It uses thresholding to determine if the person or the origin we're tracking is far enough away before the translation or the smooth movement occurs to snap it back into the place of the new follow target. What this basically means is we end up having an object that follows the user's head, in my case, very smoothly and keeps it placed into the environment. Now, the MRTK is one of the core components of Esky. So Esky leverages the very nice natural hand interactions afforded by the MRTK. So in this case, I'm going to close off the window and actually look over here to one of the demonstrations that I presented at ISMA. So I'm actually going to have to get up and grab that, bring that engine over to my desk. So what the MRTK allows us to do is, via these hand interactions and gestures, interact with the object. And I'll take a look at this engine right now. So I'll have to open up the cube. And inside the anchor, we have our engine. And as we can see, we have the near interaction grabbable script that's given by the MRTK. But what you've probably already noticed that's a little different from the MRTK is that we have this Esky anchor content script attached. Now, what this essentially does is it allows us to tag any anchor content with a content ID. Now, when the scene starts, the transform for this object will be set as a transform of the anchor. And when we go to save the map, it'd essentially save the local position relative to the anchor in the scene. So this cube here is actually our Esky anchor that's been marked for our origin. So whenever we place content in the scene and author content, its poses are always stored relative to this Esky anchor. So where this Esky anchor is placed can be arbitrary, but typically you'd want this to be placed at the 0 point of your scene. This also includes an Esky map saver basic functionality. So I'm going to do a little bit of fun here. Slap the headset down, open up my hand menu, start some spatial mapping live. With any luck, everything will work. So as you can see, I'm building a 3D map of my environment at the moment. So that way I can use this for anchoring, for authoring content into the scene later. So I'm going to quickly move my head around a little bit. All right, I think that should be enough. I should stop the spatial mapping now. Now, what I might do is every single one of these MRTK examples actually has an Esky anchor content script attached to it. So I'm going to move over and grab my engine and place that engine very high up above my head so that way I can actually see the screen in front of me. Then what I'm going to do is I'm going to save this map. Now, with any luck, this won't completely crash. So open map, save the map. Now you've noticed that my screen has already frozen once I clicked save map. That's because the Z itself has shut down and is now dumping its raw binary information for relocalization. Once this is done, we should see in the console window that the package was exported successfully. Now there are a few bugs, this being the nature of this being totally new software, but that's okay. So we'll save this map again, and this time it should be successful. So as in the bottom left, we see that we've serialized the meshes to the binary and have saved the file. The Z is still currently reloading, but once it does, it places content back into the scene and relocalizes it. So now, with any luck, I'm going to close off this Unity scene. First, let me clear my meshes. Whoop. Get my mouse back into the view, wherever it may be. There you are. And untick the play of the scene to stop it. My computer seems to have been frozen for a quick sec. Not sure what's going on here. There we go. So I've unpaused the scene. So that actually cleans up my development environment. Now, with any luck, once I hit play, first we'll see the content being placed back into the scene in its default positions. So the engine that I placed should be sitting over here. Awesome. Now I'm going to actually open up my little admin panel again and load this map. Now, the Z will freeze as a result of this because it's closed down. But as you can see, once the map was loaded and the scene was relocalized, our engine is placed back into the same position that it was in before. So this is what we call scene authoring and relocalization built into the Esky wrappers, taking away a lot of the stress for you so that we could quickly develop this environment. So I'm going to now pause that scene again, seeing as I've shown you a little bit of the code, and go back into our little PowerPoint presentation. Bringing this back up. Going to have to quickly scroll over to it because I am a noob at PowerPoint. Skip. So we've gone over the Esky authoring and creation flow. So the other component that's built into Project Esky, and one that's really heavily sought after, is the ability to create co-localized experiences. So for this, we've integrated mirror networking, which is given by Unity as part of Project Esky. So mirror networking in a nutshell, mirror networking works via a client-server based architecture. So we have clients that connect to a server and send messages to the server. The server then relays this information to clients via various synchronized variables or RPC calls, which are given to all clients, or target IPC calls, which are given specifically only to particular clients that we've tagged. Now, you actually don't need to worry about any of this unless you wanted to pass some extra scripts in, but revisiting the Esky scene graph, we have an Esky map, which includes an Esky anchor, some Esky anchor content as a series of transforms relative to this anchor, and an Esky tracking origin. Now, all of the mirror networking prefabs, so the Esky client, which follows the local user, is actually synchronized via this Esky tracking origin, as in its local pose is captured, uploaded to the server, and then passed by the clients on the other end. Additionally, for any object that we have in the scene, that we want to synchronize over the network, we include an Esky networking scene graph. What this does is any child objects that are tagged with the Esky scene graph node are then passed as local transforms over the network and then reset on the other end. So applying this Esky scene graph, we're going to take the example of Rock and Bob Boxing, which was developed by a bunch of undergrad students for the demonstration at ISMA 2020. So essentially, we have two users standing apart from each other, approximately 1.5 meters, wearing a couple of these headsets. Now, for each player within our scene, we represent them as an Esky client that has a scene graph node attached to the right-hand game object and the left-hand game object. What will happen is the left and right hands transforms local position according to the Esky client, as well as the Esky client's local position with respect to the Esky tracking origin, is sent over the network and then passed on to the Esky client on the other side. So our typical networking flow for Esky is pretty simple, actually. So first, we start our scene up. We load an Esky map into the system, so that way we can then relocalize with respect to a known tracking origin. Then you connect to a server after localization and are able to share the experience right out of the box without having to worry about what's going in the back end. Now, I'm going to make an attempt to start the Rock and Bob Boxing demo and then showcase what's going on with the demo live, but I have honestly no idea if this is going to work. So let's go with it. So I'm going to hit play here. With any luck, the Rock and Bob Boxing server is still active. All right, let me pop my head down. Load my map. So that way the anchor content can be placed back into the scene properly. And as you can see, we've relocalized perfectly. So our little engine is placed where we had it before. Now I've already pre-placed our Esky anchor on the 4. So once I click connect, we can see that the arms from the Rock and Bot boxing game have now appeared onto me. Now I'm going to hit pause momentarily so that we could take a look at the networking prefab configured by Esky. I should probably also switch over to this live view. So with this generic VR networking rig, what we have attached to it is a Esky client, which takes its local position and rotation with respect to the origin and synchronizes it to the scene. Additionally, what we have attached to this is a series of actions that are performed specifically for AR clients with respect to, like, for example, hiding game objects that we want only VR clients to see. Additionally, we have an Esky scene graph sync script. Now, what this is doing is taking all of the game objects that are child of this game object within the scene that have a scene graph node attached to it, and is taking the local positions and rotations and then passing these positions and rotations to our server. So I'll re-enable this again so that way you can see the nice hand movement. And I'm going to disconnect from my backpack PC and switch it over to what I call the Salt Shaker, which is now running the server. So bear with me one moment. Now, for those that are live via the Global XR talk, you're going to hopefully see the content showing, but I'm having a little bit of trouble windowing this. There we go. So we can see within this VR scene already, we have a robot placed into the field. So as I rotate my head left and right, the robot itself will move around. Additionally, if I was to bring my hands up, you can see that the hands of the robot move around with them. So I'm going to zoom in a little bit on the robot and move to the front. All right, now I'm going to show my hands. You can see that my hand and finger tracking is communicated to the remote server. So if I open my hand and close my hand and open my hand, move my hand this way, move my hand that way, we could see that the virtual robot on the other side moves its hands accordingly. So this is all done automatically via the Esky scene graph nodes. Now, the networking for Project Esky is severely optimized to use minimal bandwidth. And if you want details on this, I'd be happy to discuss this with you. It's actually a huge topic that's part of my PhD thesis. So I'm not going to go into detail with it now. Just know that it's handling all of this for you. All right, I'm going to move back into the presentation mode. For those that are watching via Facebook, I do apologize because the nature of the way I'm sharing my screen, you won't be able to see this, but I imagine that the Global XR talk will be available to you later. Right, going back into my backpack PC. So I'm going to stop the scene and move myself back to the PowerPoint presentation mode. I'm going to start the slides hopefully from this one. So as you can see, we've used a basic networking example, which shows how to share the pose and orientation along with the hand tracking orientations for two clients. So I'm going to go into a little bit of demonstrations now and closing and Q&A. But first, I want to just discuss what's next for Project Esky's roadmap. So really, this project was developed over the last 6 months, including a series of demonstrations that was performed by a bunch of students. And extending on beyond this, I've been a little bit slack due to the last minute slide creation. I am intending on creating a series of documentation based on the talk I'm giving now, as well as providing some stabilization techniques in order to get the same quality of the AR scene through the North Star that we can get from a HoloLens. Finally, I want to give some special thanks to some people that have supported Project Esky and have really been core to motivating me to get my ass moving to make Esky special and, giving me whatever hardware access, tidbits of advice. So first, I want to give a shout out to Noah, who runs creative. I can't remember the name of it actually. And I do apologize for this. He's basically the guy that's been building the North Star hardware, including the display driver, the optics and everything, and has been really fundamental into nailing the hardware side of this. I also want to give a shout out to Brian, who not only has given a talk already at Global XR about how to work with Project North Star, but is also fundamental in the North Star's design, the reach to the community, and really the support of bringing everybody together. Finally, I'd also like to thank the 2 advisors to the research side of Project Esky and moving Esky forward. So first, Alvaro Casanelli, who I've had many discussions with about this project, and Mark Billinghurst, who is kind of the background advisor that's been helping me out with some of the research related stuff. Finally, part of the projects that I demonstrated at ISMA yesterday were developed by a team of undergraduate students who were entirely volunteer and did this out of their own time. So I really want to extend a warm shout out to them. So that being said, this is the end of my live talk. I'm going to essentially allow for Q&A while I'm doing some demonstrations for the next 10, 20 minutes. Now, the reason mainly behind these demonstrations is because I suspect not many people are actually listening or watching and would prefer to watch this later, but that's okay. I'm actually going to entertain myself a little bit here. So really, I want to show off a little bit of what Esky is capable of. So I'll move the scene back into here. And then I'm going to hit play and start playing with some content. So one of the things that I absolutely love about this application, and it's quite famous in the video for Project Esky, and I have no audio. How embarrassing. But as you can see, we have a live piano here that I can interact with. Quite nice. But one of the core things that I'm very happy about is the fact that we've got the same capabilities of the HoloLens built into an open source headset, which includes this kind of spatial mapping. Now, I also like building cars for a living. So one of the applications that I demonstrated is the this kind of engine design so I can better understand the engine that's going into my car at the moment. So you can see I'm able to enable some sort of transparency on this object. So I can see the pistons and the gears and the gearbox rotating around on the inside. Now, of course, I can make this go a lot faster to see the engine, what it's supposed to be running at the full speed and how the gearbox itself moves. Or I can run it at 0, so that way I can take a much closer detailed look on the inside of this engine. Now, I'm going to load this map up and replace the content back in the scene. While the screen's frozen, it's not going to do anything. But as you can see, we've relocalized and placed the engine back into the scene, which I had set up earlier. Now, with any luck, the spatial mapping would work. Sadly, it doesn't seem to be, but that's okay. It's only a slight demonstration for today. Let me move this out of the way. Do some far distance interactions with the object to bring the sphere closer to me somehow. Maybe I should bring the whole thing closer to me. There we go. I can reach out and grab this globe. And as you can see, it's very nice, high quality detail. So we got this nice outer core, inner core, mantle. And we have the usual MRTK setup examples. Now I'm going to switch back into the landing page. And I hope that you all enjoyed my little talk and demonstration. I'm very happy to answer any questions and comments, even after this video is posted. Dino, I'm not hearing you over the speakers. And I'm wondering why that might be. Let me check to see what my audio settings is at. Seems to be set to the right thing. Yeah, that seems... Okay, can you hear me now? No, I'm still not able to hear you. That's disappointing. I wonder why. Having a little bit of troubleshooting. Just give a thumbs up if you can hear me. Okay, so you can hear me, but I can't hear you. That's annoying. Perhaps it's connected up to my Logitech HMD. All right, check 1, 2. Can you hear me? Still not able to hear you. Tell you what, I'll leave the studio and then come back in and see what happens.
And now? I think it was me.
There we go.
Can you hear me now?
Definitely.
I have to apologize. It was actually my fault. My mic was muted.
I'm guessing it's got one of these hardware buttons on it as well.
Yeah, exactly. It was muted in the software, but this button over here, it was muted. So I'm sorry.
You're okay. So, do you have any questions? I'd be very happy to answer.
Yeah. Actually, I have a few. There wasn't any questions in the audience up until now, but I wrote some things down. So as I was watching your presentation, which was very exciting, I was looking up and trying to find the source, and I wasn't able actually to find it.
So, I believe the YouTube link was attached to the description of the Global XR talk.
Mhm.
So within this YouTube link, there is a link to the GitHub repo. But to be honest, that GitHub repo is still in its beta stage. It's yet to be tidied up so that way, you can download the code. But it has been tested. So if you wanted a quick preview to try it yourself, feel free to grab it.
Okay, awesome. Perfect. Yeah, so my other question would be, it's pretty cool that you have a MRDK integration already. So does that mean, your demos showed a lot of basically, are all of the MRDK features, the UI, UX components, they're all working already?
So a majority of the UI UX components are working with Project Esky, but some of them Project Esky essentially re-implements in a way that makes more sense to the naive user. One example of this is this kind of solver script that the MLTK has, which
Mhm.
allows you to attach objects to a specific point, like a finger and whatnot. This sometimes doesn't work too well and is a bit complicated for the end user. So we've simplified this using Project Esky to only worry about the left-hand, right-hand origins, and therefore have scripts that follow the left right hand origins or the HMD itself.
Okay, awesome. Um, that's pretty cool. So my other question would be, if I am using so will basically using Project Esky with MREK, will it break support for, let's say, HoloLens 2 or Quest, or basically targeting other platforms, or does it still maintain the cross-platform support?
It still maintains the cross-platform support. In fact, that's the core purpose of Project Esky,
Yeah.
to essentially you develop for North Star very rapidly and then later deploy it to a HoloLens. Right now, I'm in the middle of getting access to the HoloLens and HoloLens 2 hardware, so that way I can write the same wrappers for the map saving and loading and authoring, so that way you've got this available to the HoloLens and HoloLens 2, as opposed to using the Azure SDK, which is very heavily pushed to create and content this content online. Now, of course, we don't always have access to the internet, which is
Mhm.
why Esky provides this kind of local solution.
Okay, awesome, perfect. So, as far as I understood, you have integrated networking using Mirror.
Yep.
Is that like must have, or is it possible to use other networking SDKs like Bolt, or I don't know, WebRTC, anything else, or does that is Mirror basically mandatory in this case?
Mirror is not mandatory. I've actually written the wrappers to be as lightweight as possible. My intention eventually is to move this over to WebRTC, but again, this project was really developed in the last few months,
Yeah, sure.
and we're all working outside of our usual hours. So if many people request having WebRTC involved as a package for Esky, I'm very happy to support it.
Cool, very cool, awesome, awesome work.
Uh,
Um, we actually have one question in the audience now. As I can see, we have so
Yay.
Igor is asking, can I start with MRTK with no coding experience? You want to
So,
answer that?
so with no coding experience, maybe it's going to be a heck of a learning curve, but the MRTK is very nicely designed for drag and drop development. So if you get the idea or the theory behind this kind of mixed reality development, but didn't care too much for Unity's code or C Sharp, the MRTK does provide this very nicely. And the Esky SDK built with it supports this very nicely as well.
Yeah, I agree with that. Cool. So there is no more questions actually. Thank you once again. A very interesting talk. And yeah, wrapping up, I guess.
All right. Well, ciao, ciao, everyone, and I'll see you on the Project North Star Discord.
Yeah. So